So let's move on with the next speaker, Srashti Goyal. You have the floor.
Thank you. So thank you so much for the opportunity to talk here and for a very nice conference. So I'll be talking about probing dark and baryonic matter with deeply lensed gravitational waves. And this is work done in AEI Potsdam with actually led by Guy Brando, Stefano, and Hector and Miguel, who are here. To start with, we have kind of already established that lensing in wave optics regime can give diffraction. That is, if you pass light through a slit which has a comparable size to the wavelength, then depending on the slit shape, you can get beautiful diffraction patterns. And similarly for gravitational waves, this can happen. In particular for halos, galaxies, and supermassive black holes, where the masses are quite larger than a million solar masses. There we see that the length scale associated with such lenses is like a million kilometer, which is for light is always much larger for light. So there will always be geometrical optics limit where you have overall magnification and some time delay. And also for the current ground-based detectors or future ground-based detectors, which have frequencies in a few hertz, hundreds of hertz, their wavelengths are such that these things will create geometrical optics when they're, and you will only have magnification time. But in LISA, where LISA is a space mission, which is going to be there by 2035 roughly. It will go around the Earth's orbit near the sun and will detect much in the milli-Hz regime gravitational waves, which will be having much longer wavelengths. And there, it can become comparable to the size of the lens, and we can probably have wave optics. So is some delay or what? So to more concretize the problem, let's say if we have a massive binary black hole source in LISA that we expect, which are roughly 10 power 4 solar masses going around each other, and they create strains, and then it goes from lenses like that, like a galaxy lens, and then what you see is in LISA will be a distortion. In frequency domain, you can see it like this, like the unlensed waveform and the diffraction would be, you can see distortions in the amplitude. And good thing about the sources that, especially in LISA, is that it can be particularly very high SNRs, like up to 1,000 and more. And therefore, these distortions can possibly be measured like when they're really small, that is, when the impact parameters are really large of the source. So therefore, we hope that it can be detected for a very non-aligned lens source system that is in the weak lensing regime and help us to probe substructures like supermassive black holes and some more. And here we are interested in seeing that what will be the rates of this happening. And earlier studies have implied could be of the order of 5% and so on, also by Jose, who was here, and by Stefano, and here we do it with more comprehensive. First of all, just to just to set the base, what we are having is everything in the weak field limit, that we have a source and a lens and a source and an observer, and everything is in the lens plane. And the overall lensed waveform can be written as multiplication of the amplification factor, where this amplification factor is given is this integral, where you have in the exponential the Fermat potential, which has two components, geometric and the Shapiro, this is coming because of the gravitational potential. This is fairly accepted by this, known by this community, so let me move on. And as Hector has talked about it, how to compute this f of f's in his in Wednesday talk. It's definitely challenging to compute f of f's, but we use GLOW, the package developed by him, and then in particular for the lenses or kind of systems we are interested in are black holes, galaxies, and halos. They can be modeled like a point lens, like a delta function, or like a single isothermal sphere or NFW. And as you see here, the surface density of this lenses for point mass, it's just delta function. And SIS is more steeper than usually NFW. And here you see that how that one can directly get the f of W using GLOW. And more or less, the more compact lenses like point lens and pink here, they create more features or more oscillations as compared to the extended lenses like SIS. Now, to forecast the lensing probabilities, we follow a three-step method. One is, the first thing is we want to see if lensing is really detectable. And to do that, we calculate mismatch. So mismatch between lensed and unlensed waveform, given by this, taking into account your baseline and that times the SNR. If it is greater than 1, then lensing is detectable. So this criteria will hold until some impact parameters. And until this criteria holds, that we define that it has critical impact parameter. And to calculate then the optical depths, what we'll have is that for a given fixed source, we have to integrate all the lenses which are in between source and our observer. So integrate over all the lenses in between and multiply each of them with their cross section, which is just proportional to the pi critical square, and also to the number of lenses that are there for each given mass. So this is a differential optical depth, which is everything is with respect to a mass of the lens. And then the last step is to integrate over all the source population.
Impact for, critical Y in this case. How do you define it?
Yes. So we have a lens waveform and we have a lens waveform. We take its inner product, like some value between 0 to 1, which tells how different they are. And we multiply it by SNR square, that is signal to noise ratio of the original signal. And until you change your impact parameter, those things, the mismatch will essentially be going down. So there will be some critical value until which you see observable differences. And using that, using the Hello mass functions in our optical depth here. Now, this is usually given by restricted theory or things like that. We use distinct Hello mass functions. What is shown is for, if you assume that the halos follow SIS profile, singular profile, what you see is that the optical depth, or the probability of lensing as a function of mass of the halos can be written like this. Are shown to be like this. And there you see, and it's much larger than the usual strong lensing optical depth, which just goes as Einstein radius. And then you also see that it peaks at kind of low masses of halos. So it's because why it peaks is because probably that the wave optics features are more prominent, that you have more comparable wavelengths. And secondly, the lenses are usually more abundant as you go lower into the mass. So this is also a motivation that could possibly help us in probing dwarf galaxies. This wasn't shown in Celestine. This result is from 2023, and then One could also ask that, can you really probe substructure with this? But this is a simplified model. To do substructure, what we do next is, okay. What we do next is we include, so we have a main hello, and around it there will be many sub-hellos. So we include sub-hellos, which are also dark matter. And then we include baryonic matter separately as the galaxies. So in main halo can host central galaxies, and sub-halos can host satellite galaxies. And then in center of galaxies, there would be supermassive black holes. So then the total optical depth that we have would be a sum of all these components. So to start with subhalos, the subhalos can be modeled again using subhalo mass function, which is shown here. And so for a given main halo, we'll add main halo and its mass. In again through theory, cosmological theory of how dark matter evolves, when we can have some understanding of the number of halos, sub-halos of a given mass. And using that, what we find is for the SIS case, the sub-halos follow this curve here. That is, so sub-halos can go from really small masses to until the comparable size to main halo mass. So you see it follows compared to the main halo mass, it can go the optical length go until higher masses. And if we now consider NFW, which is like, we know that from the weak lensing measurements of cosmology that at larger scales, the dark matter instead follows NFW profile. There you see that if you use NFW, the optical depths for halos and subhalos drop down by almost 2 orders of magnitude. 5% you go to point. Now, next step is to include baryonic matter, and to get baryonic matter, we use that what is the mass of the galaxy given mass of the halo, and this we use Taylor to peak halo mass relation, which is given in universe machine code by fits to the real data, and using that. When we compute also the number of galaxies given of a given mass. And as you see here, we do this both for central and the satellite galaxies. So you see here for a particular halo mass, we can get number of halos, number of central galaxies that it has, and roughly follows actually the halo mass function itself. And also for the subhalos, one can do that. Here we have just one condition, that the masses cannot go of the galaxy beyond 10 bar 8 solar masses. And the size of the galaxy is 2% the size of the halo. Finally, the last ingredient is supermassive black hole, which is modeled like a point lens. And it's in the center of each galaxy and has masses of 1% of mass in the particular galaxy. So, plugging all these things in, one can find optical depths by using the mass functions and finding cross section for each kind of substructure based on their masses. And with this, what we find is the following. So, first of all, we use NFW for this result. NFW for this result. And you see here that compared to SIS, the NFW is 2 orders of magnitude smaller than SIS. And then we also see that for galaxies and central galaxies, the function of host mass or the optical depths, they are actually smaller than that of supermassive black holes. So supermassive black holes have higher optical depths, and it's actually even higher than NFW halos here. So in total, if we see here that the sum of the substructure, assuming NFW halos and galaxies, and then SIS galaxies, and then supermassive black holes, is roughly 1 order of magnitude smaller than if you just compute everything by assuming that we just have SIS halos. Now, coming to the source populations, we take two approaches. The first one is the agnostic, that is, let's say we vary the mass of the source, the massive binary black hole, over here, and then we vary its redshift. So all the results I've shown till now are for a given fixed source. Here we vary the different sources and see how the optical depth changes. And in the approach where we have substructure with NFW halos plus galaxies plus supermassive black holes, as we shown, the probabilities are dominated by supermassive black holes. And also, if you see here the contours here, it goes, the dashed lines are the SNR contours. And we see roughly that the optical depths are actually following quite nicely the SNR contours. So they are quite proportional. And on the other hand, for SIS, you see like the optical depths are much higher, and they also follow SNR contours, but not as tightly. Moving on to next slide. The second approach is to use formation channels, that instead of using uniform or instead of being agnostic about what is the source, we use population model. And for the population models, there are light and heavy seeds population formation channels for LISA. So light seeds are basically kind of the first stars, the remnants of the first stars that form at very high redshift. And they'll have masses usually more than 10 power 4 solar masses, around 10 power 4 solar masses. And they form binaries and can merge and can be visible in LISA. And on the other hand, the heavy seeds, they are more massive. They are formed by just direct collapse of protogalactic disks, and they can also, in principle, merge and give gravitational waves. So this POP3 is this light seeds where you expect slightly smaller masses, and then heavy seeds are over here. And these are the two different versions of heavy seeds, the one which does not include the time delay between the formation of the binary and their merger. And this is the one when you include it. So here the numbers drop down because many of them don't merge between the Hubble time. So overall, we apply our framework to this source populations and see that the most promising is actually heavy seeds without any time delay, where you see 1 out of 500 can be lensed. So roughly what we find is that 0.1 to 1% of massive binary black holes can be lensed and detectable in 5 years of LISA mission. And these rates are actually not to be taken too literally, because they increase if you rather model your halos or subhalos as SIS profiles. So they'll increase at least by an order. And there are some more modeling uncertainties. So for example, if you change the inner concentration of the halos, which are not really known for smaller mass halos from observations, if you say that they're more compact, then also the optical depths increase, and they can go almost as high as the one that we get from SIS. So the things which are here really in this slower regime where things are more dark matter dominated, it's a bit of uncertainty in the literature, and this can in principle be used to test dark matter theories also. And second thing, there are some other modeling uncertainties that we use some numbers like 1% of the SMBH mass is in the 1% of the baryonic mass is in the form of SMBH. We see that if we change that ratio, the optical depths scale linearly, And similarly, about the size of the galaxy, we assume that the galaxy is roughly 0.02, then of the size of the halo. Then if you make them more compact, again the probabilities increase. Now, here is one thing that why do we think that our modeling so far is conservative, saying that 1% is detectable. And this is also because the NFW halos plus SIS galaxies that we have been using, if you extend it to strong lensing limit, that is when that would happen when you have very high halo masses, and things would be given by the Einstein radius of the profile of the objects. There you see that they are actually underestimate the probabilities which you would get from just the SIS profile with the halo mass function, so the black one. And this one has the SIS with the halo mass function has been shown to in the EM literature or with the hydrodynamical simulations of the universe, they have been shown to with the ray tracing algorithms in the Robertson world, they have shown that the optical depths are closer to the SIS halo one. So overall, we say that it's conservative, that it's not really, our model is not really very set in stone. It does not predict the correct optical depths in the strong lensing limit. And this is also a thing, like strong lensing is sensitive only to the mass inside the Einstein radius, whereas wave optics, you probe up till thousands of Einstein radius. So it's true, like SIS, people have shown that the total matter profile inside a bulge, galactic bulge, which is roughly also the size of the Einstein radius. The things are isothermal, that is, they follow r to the power -2, but then if you see the individual components, dark matter and stars, neither of them really follow r to the power -2. This is known with some EM galaxy lensing matched with the scalar dynamics, and not an expert on this. So one of the possible things is that instead of baryonic matter like following SIS, they're actually more steeper, as you see here. And this could probably, this could give us a possible enhancement in our probabilities. And the other enhancement we could expect is from asymmetrical lenses. That is, so far we assume that everything is isolated and axisymmetric, but in reality, what we have is really that the subhalos, central satellite galaxies are all sheared, and they can they can give enhancements. So here is one of the example where this is the main halo and this is the subhalo. And if you were just, so this is the source, which image, which is closer to the subhalo. And if there was no main halo, what we would get is this f of w. But in the presence of the main halo, the wave optics features are actually very enhanced. So this could also be a possible enhancement to explain the optical depths that we would see, or rather to probe the universe structure. And these are finally the conclusions. So we overall see that gravitational waves from massive binary black holes in LISA can be weakly lensed by the dark matter and the baryonic matter, and we predict roughly 0.1 to 1% of them to be lensed, depending on the source population model. And our model is conservative if we rather model halos as SIS, or even with like steeper density profiles, the probabilities will increase by an order of magnitude. And as I showed, like lens models can be further improved by including asymmetry and more realistic profiles for baryons. And further, hopefully both observation and non-observation can be used in future probably to constrain dark and baryonic matter in the universe, especially at the low mass scales where EM lensing is not very sensitive to. And finally, we would actually require parameter estimation study to distinguish different types of lenses that are there. And hope it can be done using GLOW also, but it would also require LISA PE, which is also very slow at this point. And it's something to look into future. Since I have time, there is also a trailer. So there's something beyond LISA, which a committee has been formed to really plan something for 2050, a space mission for 2050. And there are, in different frequency regimes, there are different space detectors that could be built. So LISA is like around the sun, 2.5 million kilometer arms. There is a deci-Hz observatory which is proposed, which can have 25x smaller arm lengths and can probe like 10 power minus 1 10 power minus 1 frequency regime. And there is something more ambitious is the LISA Max that have a detector which is having three, almost as like size of the orbit of distance from the Earth and the Sun. So this is 100x larger arm length than LISA, and it will can probe the micro-Hertz regime where you can go much lower than LISA. But here there was a catch, like there is a lot of galactic background that's there when you go to micro-Hertz. So what you gain is roughly more in 10 power minus 5. And so this is the gravitational spectrum that, with all these detectors, what are the sources we would expect. So lower in the frequency, the more massive binaries we would be able to probe. Now we just thought that, okay, let's see what is the probability of lensing, of weak lensing for different detectors. And using the framework of, let's say, SIS with hello mass function and NFW with hello mass function, what we see is the following. So this is where the LISA is looking with SIS like this and wave optics like this. And with deci-Hz, we see that it can go even lower in the hello masses, like you can probe even lighter hellos. And whereas for LISA Max, which is the micro-Hertz regime detector, it has really it has good probabilities. You get like roughly 7% in case of NFWs and roughly 50% in case of SIS hellos. So there's a possibility that if it really flies, we'll see something and be able to. And these are the curves just for one sources, and we would need to include source populations to really claim what kind of detectors are best in context of lensing, and also include galaxies and supermassive.